and welcome to Physics Society, and welcome to the first talk of Nicholas' term. My name is G, and I'm the president. Here's Alex, he's our treasurer, Rob, our IT officer, Yekwan at the door was our publicity officer, Alda here is our academic officer. Welcome, and we'd love to welcome our speaker, Professor Vlatko, for his talk on quantum physics meets general relativity.
Thank you. Thanks very much. I think I'm sufficiently wide that you can hear me. I probably don't need this kind of stuff. So it's always a great pleasure to speak to colleagues and soulmates. These are my favorite kind of talks because I know you're here really because you're interested in this. It's not part of the undergraduate course or any other. No one is really forcing you to be here. That's always nice to know. So what I wanted to talk to you about is something that I thought you wouldn't naturally hear if you listen to all sorts of debates, online debates, or even if you go to other lectures and discussions. Most of the time you'll be hearing that general relativity and quantum mechanics are extremely different to one another, to the degree that people always say you can never reconcile these differences. We haven't quantized gravity yet. And actually there are people who say it's never going to happen, really. There's one view of that kind. There are people who say that you will have to really modify one of the two theories or both of them sufficiently to fit them into something together. And what I want to tell you tonight is the exact opposite. I want to go in the opposite direction because not many of us are saying things like that, and it just so happens that it could be that we're on the brink of testing many of these things. So the reason why I'm excited about this is precisely because quantum technologies over the last 20 years have brought us to a point when we can really test this common ground of quantum mechanics and general relativity. And then it matters what you think about two theories. What kind of views you have about them determines what kind of experiments you'll ultimately be pursuing. And even though at present none of these views are really distinguishable from one another, they are kind of 2 to the power of n different quantum gravity roads, if you like. We have no idea whether any of them make sense, really. But the exciting thing for a physicist really is that we can start to test them now. And that's what I want to tell you about. So I never lecture with slides and stuff like that, and I hope it's okay that we use this kind. I won't be writing too much. I think most of the time I'll be talking. So let me set the scene already with special relativity. Now, most of you will know that special relativity and quantum mechanics have been united, and we call it quantum field theory, and that's what we call the standard model now. It's the best description, includes everything. Everything is quantum in that model other than gravity. So that's kind of the big outstanding. There are many other questions. But many people feel that even quantum field theory is kind of phenomenological. It's not the ultimate description of reality. So even in quantum field theory, many people feel uneasy. And they say, well, even special relativity and quantum mechanics don't really necessarily go well together. There are all sorts of issues we're experiencing. So I want to give you that kind of intro gently, and then we'll go to GR. And then at the very end, I'll tell you what I think about the similarities. And they're interesting, they're surprising, and I don't hear many people talk about these things. So actually it may be easier to unify the two than we think, but what's absolutely missing is any experimental evidence as to what we should be doing. That's just clear. It's the experiment that's not guiding us at all, and hopefully in the next decade or so this will happen. So I want to tell you about this apparent paradox. Remember, whenever you hear a word paradox in quantum or in relativity, it's not a paradox. It's historically something that people thought was a problem, like the twin paradox. But actually we've tested it so much now that we know that's how nature works. The same with EPR paradox, anything to do with entanglement, with measurement, there are no paradoxes. These two theories work beautifully in their own domains. Absolutely no disagreement whatsoever. But let me tell you what some people feel uneasy about, and you may hear a lot of discussion about this. Some people call it the Andromeda Paradox. It's really a version, it's a kind of sexed up version of the twin paradox, as though twin paradox needs, by the way, sexing up. It's already mind-blowing that this happens for real, and we know that from all sorts of atomic clock measurements and so on. So basically the Andromeda Paradox is the following one. And people who, it's a special relativistic effect. Like I said, it's not a paradox. But people claim that that goes 100% against the spirit of quantum mechanics. And I want to claim the opposite. I think special relativity owes it to quantum mechanics. If the universe wasn't quantum, even special relativity would be in trouble. And again, this is a statement you don't hear many times. And already here I want to explore these parallels between the two. So, what is the Andromeda Paradox? You have a very distant planet. Andromeda is just a name that probably is catchy, and that's why people call it like that. I usually just choose a random star that's far away enough for this effect to be significant. And the statement is the following. You imagine that there is an alien army on Andromeda deciding to invade us on Earth. So all the top generals on Andromeda are sitting down, the war room round table, and they're about to decide, let's send the troops to Earth or let's not do it. They haven't decided yet. And so what's the stunning statement from special relativity? You've got two people on Earth in this lecture theater, and one of them is gently strolling towards Andromeda at 1 meter per second. Very slow. I want to tell you that relativity still matters, even at speeds as low as human speed of walking or jogging or whatever. The other person, I'm going to contrast two frames of reference. The other person is walking in the opposite direction. Imagine Andromeda is somewhere there. They are literally passing by one another, and I want to stop at that distance when they're really standing almost at the same physical location. Okay? They could define that as their now. Each of them are experiencing the same now. And the stunning thing in relativity, because they may be moving at the same speed but in the opposite direction. And if you remember Einstein's train, the person on the train, what they see as simultaneous, two flashes at the either end of the train, and the person standing right in the middle of the train, and the light arrives at the same time, won't be seen like that from the platform, because the person on the platform sees the train move forward, and therefore the light from the front will reach the person in the middle faster than the light from the back. Simultaneity is not an absolute in this universe. It's absolute for Newton, but not in special relativity, and not in nature, we know this. Now, what does Andromeda Paradox say? And this is the stunning thing. If you look at the guy walking towards Andromeda, his now coincides with the generals already having decided whether to invade. His now is simultaneous with the generals saying, let's go for it. Yeah, let's invade them. They can't defend themselves. The person walking in the other direction, their now is before that. Their now coincides, that's why I need a galaxy that's far away, because their speeds are so small that I have to go far enough that I get a difference in these two nows. Their now, walking away from the galaxy, coincides with the moment before the generals even sat down to make their decision. Wow. I mean, stunning. There is special relativity. It's really amazing, but they're standing in the same location on Earth. It's just that they're passing by. They belong to two different reference frames. There are Nobel Prize winners who don't think that this is right, by the way. They just haven't grasped that this is what special relativity is telling us. And it is like that. That's what it is. Now, Einstein loved it, by the way, because for him, this is what makes us feel that things that are about to happen in some frame, they're in the future, they could actually be in the past for someone else. So Einstein kind of had this block picture of the whole universe. Everything that will happen, that has happened, already exists in this four-dimensional universe, and we're just walking through that. And one event becomes the now, then the now, and so on. It's a very static, fully deterministic, and that's the key word now, I said it, deterministic picture of the universe. It's a really stunning, it's actually a variant of the twin paradox. I didn't do anything than just did half of the twin paradox in special relativity, but somehow it's amazing that not all observers agree on the simultaneity of events, and that's the key of this theory. And Einstein, incidentally, and some of you may know that, when his best friend died, he wrote a letter to the wife of his best friend to use special relativity to make her feel better at that moment. I think that's what we physicists think happens, actually, right? Whenever I have any trouble in my personal life, I escape to physics, and it always works. I highly recommend it. Just do it, ignore everything else. So he said to her, he may have died for us in our reference. He said it more poetically and beautifully. I'm paraphrasing in my own ugly way, I think. So he said, for us in this reference frame, your husband may well be dead. But remember that there is another reference frame in which someone may see this order of events in a different way, and I think he was trying to give this kind of static picture in which nothing really gets created or destroyed, it just exists throughout the whole of eternity. And that's kind of the spirit of special relativity. Now I have a better version of the Andromeda Paradox. Of course I would think I have a better version, right? But it's better because I'm going to try to now make it as hard as I can in conflict with quantum mechanics. And here is the variant, much simpler. There is a guy on Andromeda about to send a single photon through a beam splitter. It's dead easy. It's the simplest quantum experiment you can do, okay? So the guy is sitting on Andromeda, and it's sending a photon. So let me choose one of these, hopefully that's visible enough. Sending a photon, here is a beam splitter. You know, the photon goes one way or the other. There is a detector here, and there is a detector there, okay? So why does this now seem to be different to the uncertainty that we had when generals were decided? Did they decide or did they not decide? How can two people standing in the same spot feel completely differently? For one, it's uncertain whether they will invade. For the other, the now coincides with already the decision being made. Now I'm going to make it spookier. And it's spookier because in quantum mechanics we know that there is no way of telling which of the two ports of the beam splitter the photon comes out. Okay? So you can't escape in Einstein's level. You can't say it's all predetermined anyway. The order just matters for the people moving at different speeds, but actually all of these things already pre-exist. No, this guy doesn't pre-exist. It's interesting, right? And this is where people think. So basically, imagine that for the person moving in one direction on Earth, the photon has just come out of the beam splitter and it's sitting in a superposition of two different directions. It's literally, as you would write it, let's say it's going left plus going right, even with an equal probability, at the same time. It's a superposition. And I don't know, and I'm telling you that nothing in fact, Heisenberg says you cannot know. You'd be violating Heisenberg uncertainty if you could predict which of the two detectors will click. No one knows. God doesn't know which detector is going to click. But for the other person, the person moving towards Andromeda, but standing in the same spot, one of the detectors is already clicked. For him, the time is later on Andromeda. Again, the relativity of simultaneity. And for him, let's say the detector, let's call this the detector left and the detector right. Let's say the left detector has clicked. So how can that be? How can that be? How can these two people have completely different views about something? How can one person know the outcome of a quantum measurement while the other person says, no, 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 it's unpredictable? But it's already happened in the other guy's frame. They're standing exactly at the same spot. They're just moving past each other. Mind you, this is why I love physics. This happens to be true too, but there's no paradox here whatsoever. But you can see that it makes many people nervous. And rightly so. That's the way you think about it. You try to really argue and so on. Now, I'll tell you why there isn't a paradox as far as I'm concerned. And that's the beauty of quantum mechanics. Something you never hear in your quantum course. I wish I was told this at your stage even earlier. It's not only relativity that's relative. Quantum mechanics is relative as well. And in a very interesting way, the way that matters for this. The state that you will assign to the same physical system is relative to the person assigning the state. Wow. What? Quantum state is not an absolute objective reality? No, it's not. That's the whole point, actually. And you will have many people who will assume otherwise, and they will get into all sorts of mess and apparent paradoxes and so on. So what's interesting, and why am I saying this? I'm saying this because it was already clear to people like Schrödinger. And the whole point of Schrödinger's cat paradox, it's not a paradox, right, is that there is a difference in perspectives depending on whether you interacted with the quantum system or not. And that's all there is to it. There's absolutely no violation of anything when you combine quantum mechanics in this way. And I will show you. So basically, the way I like to think of a measurement is really to think that the detector itself should be quantum. And these are the things that we are testing more and more people are getting Nobel Prizes for showing that even macroscopic objects are quantum. And I have that bias that everything is ultimately quantum, and it's the only way to understand the universe. I wrote a whole book about it, by the way, coming out in a couple of weeks' time. It's at a very low level for you guys. It's a popular book, but if you're interested in more of these discussions, you can read it there. But I think I'm telling you something far more interesting than I managed to communicate there. So here is the detector initially. So as far as the detector is concerned, before the photon enters either of the two detectors, the photon is really in a superposition. And that's the state of affairs as far as one of these people is concerned. That's before you got the detection in one of the detectors. Now, what would Schrödinger say after the detection? Well, you would have a state which is an entangled state. And this is exactly where the relativity of states now becomes important. And relativity of states is what I think saves special relativity and the relativity in special relativity. No one tells it to you like that. Quantum mechanics is not in conflict. It's rescuing various bits of classical physics that wouldn't make sense on their own. That's my paper. I know it's a strong take, not everyone agrees. But that's the summary. So basically the state after the detection is that the left photon is going to trigger the left detector. You're going to get a click in the left detector. And the other photon, on the other part of the photon to the right, is going to trigger the right detector. And that's something we call an entangled state. And that's what Schrödinger says is the whole point of quantum. He introduced the notion of entanglement. He then went well beyond detection, as you know. He so over-dramatized it that he imagined the cat being the detector. And the observable, the eigenstates of the observable are being dead and alive. It doesn't get more dramatic than that. There are two orthogonal eigenstates, according to me. But we don't need that. It's not even relevant whether this is true and it applies at that level. Just think of an ordinary photodetector. As far as this detector is concerned, the photon has entered that detector. This detector would say the state of the photon is in the left arm of the output. It's relative, the state. The state for this detector is the right state. And the state for someone who hasn't gone in, that's Schrödinger's point again, is all of these are variants of Schrödinger, is literally the state I wrote down. You have to acknowledge that this whole state is the right state. It's just an entangled state of two photons. And each of these now corresponds exactly to your two observers, thinking what's simultaneous with me now on this Andromeda galaxy. Am I simultaneous with the photons still being in a superposition, or am I simultaneous with the measurement already being made? And there's no contradiction. It's okay to have both. Quantum mechanics allows all of this. That's interesting. So I'm kind of trying to push it as far as possible to arrive at some kind of conflict. And I always found it frustrating. I looked at all of these things where people say you can't do that. You can't quantize gravity because of this, this, and this. And I just think none of this makes sense, actually. I think we're okay. We know how to do it. The question is how to test some of these different ways of doing it. All of them could be correct, but it's certainly true that we need to do something about it in the quantum sense. So let me go a little bit now into the, I hope this was okay. This makes sense so far. I tried to really explain it even if you've never done special relativity. Really, the only thing to keep in mind is the lack of uniqueness of simultaneity. What I perceive in my frame as happening at the same time, someone moving with respect to me is not going to agree with me. And the general statement is if you have two events that are space-like, which means no light can go between them, they're so far apart that light cannot reach these two events, then observers can see them in any order they like, depending on how they move. Yes?
Sorry. Can I just ask them, would you say then that the act of like being in a particular reference frame is like a state itself that is entangled then with perception? So like being in the frame is the state.
You're way ahead in many ways. Yes, I would say that I'm using the language of reference frames because that's how we learn these things. And I even talk about observers. You know, here are two people walking by. Physics doesn't require any of this. These systems need not be complex at all. So when I say a reference frame, it could be simply an atom moving at a certain speed with respect to another atom. And we can do the whole analysis completely ignoring sometimes people put too much emphasis. They think physics is all about observers consciousness. Nothing. Physics requires zero extra assumptions about observers. Literally, observers are just other physical systems in this picture. And I think we can account for everything. So that implies exactly what you are asking. That even if you call them reference frames, they can interact with your system. They can even get entangled. If you call these detectors reference frames, look, they're joining in as part of this fully quantum mechanical state. So I really, the main message is that the only way to account for all of these things consistently is to really quantize everything. The story is only consistent if everything is quantum. And it's interesting, no one tells you that. As soon as you sneak in a genuinely classical world, you're going to make a mistake. You're going to make an assumption that when I make an observation, that observation is true for everyone in the universe. And this kills the idea instantaneously. All our experiments so far have just gone against that idea. And that's very interesting. That just is hugely interesting to me. So no observation in quantum mechanics is ever definitive. It's always Schrödinger's cat. That's interesting. And now I'm going to go into gravity and tell you that there is no reason for things not to be like that with gravity as well. And this really is mind-blowing. And I'm telling you these guys because I'm really hoping that one of you will be the person to test these things. We're so close to this. And I think we have the right technology. It's just about, these are really difficult experiments because you're talking about massive objects and keeping them in superpositions for long enough that you test these things. Here is GR. Very briefly, GR. Okay? Doesn't matter if you've ever done it. So, special relativity is all about moving at constant speeds, inertial motion. And Einstein had the following genius idea. I mean, needless to say, the guy was a genius. He called this the happiest thought of my life. The happiest. This is a guy who had countless affairs, was married twice, had 3 kids. Forget about all of that. The happiest thought of my life. What's the happiest thought? If I'm falling in gravity, he imagined this lift, that you are standing in a lift that's in free fall. Why lift? Because he wants to prevent you from looking outside. That's the kind of equivalence principle. Okay? But the stunning idea is that when you are falling in gravity and nothing is resisting this, you are actually an inertial observer. Newton is spinning in his brain instantaneously. Newton would say, no force is acting on you. That's inertia. Constant speed or whatever, it's all relative at that level, but it cannot be that you're going to be accelerating and you call that inertial. Einstein says, I disagree, that's inertia. I'm in a lift. And it makes sense. It makes sense, obviously, you know, he was 50 years ahead of time. Anyone who went to space knew immediately that being in free space out there, floating and all of that, is a perfect inertial frame. What's the logic there? Well, if you're in a lift and you conduct any experiment, you put an apple next to you, it's just going to be falling down at the same speed as you. It's going to be completely inertial. Right? Anything in your vicinity, it's going to behave as though there is no force until you hit the ground and electromagnetism kills you, as you know, no gravity. So then obviously, when you imagine you're falling infinitely, everything is hunky-dory. You don't know you're falling. But this is only true locally. So that's one footnote that I want to add. If you wait for long enough, and if you're really falling in Earth's gravity, the 2 objects that you have, 2 apples that you just let them drop, let them fall with you, are now going to be attracted with you towards the center of Earth. So you're going to very quickly figure out that they're not just following a straight line, but they're actually getting closer and closer. And this to you would say that you're not just ordinarily accelerating. It's not that someone is pushing the bottom of the lift and accelerating, but you are really in a gravitational field where there is a center of gravity and everything is going towards the center of gravity. So according to Einstein, you can eliminate it locally, but if you wait for long, if you make your experiment less and less local, more and more global, you will actually realize whether it's gravity or not. But locally, strictly speaking, there isn't. The best way to cancel gravity is simply just to go with the flow. Don't resist it. Don't resist it. That's called inertia. Now, here is the ingenious idea. So, you will all know from various movies, I guess, and I want to explain it, and I'm only going to be using special relativity. Again, why doesn't anyone tell you these things when you learn physics? I have no idea. We don't teach it very well, because that's always the problem. So basically, why standing closer to a gravitational object in a stronger gravitational field, why does that lead to slowing down of time? the gravitational time dilation, not the special relativistic, but purely because there is gravity. You've all seen Interstellar, countless other movies. You're standing on a neutron star, it's half an hour for you, but your daughter is now basically on her deathbed or whatever was the dramatic element of that movie. So that's a huge difference here. How would Einstein explain that? Well, it's all about special relativity. It's actually mind-blowing. He would say, you know, here is the Earth, here is one height, and here is another height. And in each of these heights, locally, according to his happiest thought, you're just inertial. Special relativity is okay. But what you need to do is you need to constantly be free falling. So this is a very funny picture, one way of imagine, of course that's not how nature does it, but it's a way for us to imagine what space-time does, is you take a clock and you let the clock fall down. But you don't want to let it fall down too much, it must be local. As soon as it falls down a smidgen, you take a new free clock, it's going to be an awful lot of clocks, and you substitute the previous clock. Then you let this guy tick a smidgen, take the next clean clock, synchronize with this one, let it continue. It's continuously falling at this height. And that, Einstein would say, inertia. There's no gravity there. You're just free falling. The same at the other height. Okay? So this is some difference in heights, and this is the Earth down there. And the same here. You define your local frame which doesn't have gravity, it's an inertial frame, by simply letting the clock fall down continuously. And here is the ingenious idea. How do I compare the clock over here with the clock over there? You guessed it. Take another clock and just let it fall in gravity between the two clocks. What a genius idea. Zero mathematics. I'm almost doing zero. There's no tenses and all of that stuff. Amazing. Amazing. The guy was very clever, obviously. So this clock is falling down. Free fall. It's another reference frame. And in each instant, it's a reference frame, but it becomes less and less compatible now because it's only locally a reference frame. Now I'm going to let it fall for a finite height h. And imagine I synchronize the times initially here. Imagine it's zero velocity. I drop this third clock literally with zero velocity initially. It reaches this point here with a velocity of square root of 2gh. Just from energy conservation, mv squared over 2 equals mgh. That's simple, high school physics. And now Einstein says, but all of these frames are just special relativistic. If I want to know the time difference between this clock and that clock, it's governed by exactly the same 1 over gamma factor that you get in special relativity. And 1 over gamma is the square root of 1 minus v squared over c squared. And if you substitute this v here, you will get what we call Schwarzschild metric in general relativity. Okay? So that's the logic. He says, I can always compare things between two different special relativistic frames, but what I need to know as I move one clock from one location to the other, I need to know what gravity has done to it. And here I'm using a shortcut, and I'm saying we know what gravity has done to it because we can simply use very basic energy conservation, the kinetic and the potential energy. And so this guy automatically tells you, you can see that this number is always less than, this number here is always less than 1. It tells you that the clock here is ticking slower than the clock up there. But all I've used is special relativity and a little bit of conservation of energy straight from Newtonian gravity, really. It's a mind-blowing idea. It's really amazing. Hold this thought, because it's exactly this structure that I want to claim is the same in quantum mechanics. And that's the surprise. This is where I think we could go a bit more to explore. It's not going to be about gravity in quantum mechanics, but I will show you that at a higher level of logic and information, the two theories are very similar in how they operate. So all that thought for a second, I'm going to get there. But what makes people nervous now here when it comes to quantum mechanics? Well, what makes people nervous is to ask, what if you didn't have just one gravitational field? What happens to the equivalence principle if you have a superposition of a massive object? And that's something we haven't tested. That's the first experiment we need to do to clinch this question whether gravity, at least at some basic level, does have quantum mechanics. I'm betting everything I have, the whole of my overdraft, is basically going straight into betting on gravity being quantum. All of these other people are going to be wrong. And I'm not the only one betting on that, of course. Probably in some fields, majority of the people will be betting with me. So what's the problem? And it's going to go back exactly to the state I wrote before. What happens if I have a gravitational field which is in a superposition of two different gravities? So that's what you need to now imagine. You say, okay, I have a mass in a superposition of two different places. This is one massive enough that it generates big enough. Of course, even a single photon already does this for you, but the effect is so tiny from a photon that you're never going to be able to measure this. So you need something significantly larger, more massive than that. And if you put an object like that, and if you ask what's the gravitational field at some distant point, you will realize that you're going to have to add up. So now I'm imagining we're still at the Newtonian level, and I'm saying at a single point, there are actually two gravitational constants that I need to take simultaneously in a superposition. That's what quantum gravity presumably means. And it's in a superposition of G1 and G2. What's going to happen to a test mass? How is it going to respond? And there are many people who say, well, that's what quantum mechanics collapses. Why does it collapse? Because general relativity can understand how to implement the equivalence principle in one field or another field, but a superposition of two fields, it's going to be confusing. Something has to go, in a way. And I think this is a bad argument. This argument doesn't make sense. What really ought to happen, if gravity is the same as all other forces, is that the mass simply, initially, let's say it's positioned at some state, x, at some height, if you like. What really happens is that it falls simultaneously, like anything else in quantum mechanics, at two different rates, G1 and G2. And yes, you guessed it, it's Schrodinger, it's always Schrodinger. All quantum experiments are Schrodinger's experiments. They may be just slightly more complicated and intricate. But what's going to happen to a massive test object is that the state after a while will be position x1 that corresponds to the gravitational field G1. That's what it means, the equivalence principle. I've got a superposition of lists, according to Einstein's kind of educational model. And here x2, G2. And that's what we need to test. Is it really like that? Does a mass in a superposition generate a quantum mechanically ambiguous gravitational field in a superposition? And if I bring another mass in, will it really just join in a superposition? You can really think of this mass as detecting the field. So, you know, if you're thinking of a wave packet, I can draw it for you. If this is the direction of gravity, but you just have two different g's, then what happens initially if you make a wave packet, if you make some quantum mechanical state or whatever, you're dropping the Bose-Constant. These are Galilean experiments, but with quantum mechanics. You're literally standing in the Tower of Pisa. People are doing this in various labs, and you drop a Bose-Constant. What's going to happen? And what you're really testing here is whether you're going to get an entangled state where if if G1 happens to be the strength of gravity, this guy would have gone a certain distance, whatever the distance is, right? G1 t squared over 2. And in the other case, it would have gone a different distance, so these two states would ultimately result in a completely non-overlapping Gaussian distributions, if that's what you start with, of wave packets. And that's it. So is it like that? Is gravity like that? Is the big question. No one has done this before. And what it really excites me about quantum technologies is not whether we have quantum computers, whether we can all play quantum games or whatever else save humanity. Physicists never care about that, really. In all honesty, if we're honest, what we really care about is what was God thinking, you know? How did God, metaphorically speaking, create the universe? Was it really like that? Was there any other choice? Was anything else inconsistent, and so on? So this is the big question. So let me now, last 5 minutes, I want to really tell you now why I'm saying that quantum mechanics is not all that different, actually, in its intrinsic logic to relativity. So what relativity does is the following. I think the best way is maybe to even draw something like a curved geometry. So Einstein says space-time is really like a curved manifold. It's not Euclidean. However, again, the happiest thought comes in. If you're only exploring a tiny region of this curved manifold, it's going to be flat for all practical purposes. You can't detect gravity in your vicinity. You can only detect gravity at the distance. That's what gravity does for you. So it makes these two trajectories that are far apart come closer and closer and closer in the falling lift. So it's locally perfectly special relativistic, and I can actually approximate this curved manifold with a lot of infinitesimally close Minkowski, as we call them, flat spacetimes. And then when you move from one of these to the next, you need to know what gravity does. And gravity is exactly that. How you patch together flat surfaces, a bit like a football. Each of these pentagons is flat, but we sew it together and it's actually a ball, it's curved. That's exactly the right image for GR, for space-time in general relativity. Okay, that's kind of the mathematics behind this. How about quantum mechanics? How is quantum mechanics like that at all? And the beauty is and what I think should be emphasized more, is in the following. In quantum mechanics, you can think of every observable as defining a classical world. Anything that commutes with a certain observable, it means it can be measured simultaneously, is for all practical purposes classical. You're never going to get anything quantum unless you engage non-commuting observables. First I measure X, then I measure P, and then I swap this, and I see that it's not the same outcome. Your basic Heisenberg's uncertainty. So this is beautiful. And there's a statement from Heisenberg which says something like this. You can see the world with the X glasses, or you can see the world with the P glasses, meaning momentum, but you can never see the world together with X and P. It's the Heisenberg uncertainty. Now here's the beautiful analogy. Think of these classical worlds as Minkowski, flat spaces. So I'm abusing the language a little bit. But I'm saying, think of the analogy between GR and quantum mechanics in the way that what we consider special relativistic without gravity is the equivalent in quantum mechanics of the classical domain. These are observables that all can be measured simultaneously. So you can have, as you know, with quantum bits, for instance, you can have states 0 and state 1, which are orthogonal. And if you were only operating with 0 and 1 and never made any superpositions, you'd be as good as classical mechanics. That's your classical logic. That computer is never going to do anything more than a classical computer that we use. Now think about another set of observables. Instead of what we call Z, think about X. Think about 0 plus 1 and the orthogonal state 0 minus 1. That's also a good classical world. If I never do anything other than 0 plus 0 minus 1, and I only operate with these two states, I'm as good as classical. So 0, 1 is a good classical world. 0 plus 1, 0 minus 1 is a good classical world, but together, they are not a classical world. You cannot get from one to the other by going fully through classical worlds. Something is going to have to curve you away from classical logic. That's the interesting thing. So it's a way of looking at, I learned this from a guy called Chris Eischen, a great researcher, retired now, researcher at Imperial. He taught me quantum mechanics, and I think I was very lucky as an undergraduate there to listen to a crazy person like this, which I think explains the rest of my career. So, and what's the punchline? The punchline is that you could think of falling now, the analog of falling in a lift between two different flat spacetimes, as moving, rotating from the 0, 1 classical world into 0 plus 0 minus 1 classical world. And if you want to preserve this classicality, there is only one transformation that does this for you, and it's called the unitary transformation. It's exactly what the Schrödinger equation gives you. I'm now deriving, that's the amazing thing, I'm deriving quantum mechanics by making analogies with GR. But what in GR, the role that's played by geometry is now played by logic. What's classical and what's not classical, what commutes and what doesn't commute in this logic. So basically there's a beautiful theorem by Wigner saying if you want to map orthogonal distinguishable states at the beginning of your evolution into other orthogonal distinguishable states, exactly like the two sets that I chose, the only transformation that does that for you is a unitary transformation. And we know this is the most general transformation in quantum. That's all quantum mechanics is basically unitary dynamics. And to me this kind of suggests that we are unfairly saying that the two theories are very different to one another. I think if you look at them with respect to what we consider classical in one case, which would be Minkowski, special relativity, and in the other case, classical really means classical Newtonian physics, then somehow they deviate from these things in a very similar way. And I wish I could tell you more, because I'd be the person who's quantized gravity there, and it would be very good for me, of course. But like I said, I think what's missing, and the reason why we don't quite know how to do this, is simply because we have no experimental evidence, even at the lowest level that I presented 10 minutes ago. But I think we're very close to that. It's really an exciting time to be a physicist. Thank you. Thank you.
Professor Vlatko for your talk. We're just going to take questions for around 30 minutes, so if anyone has a question, please raise your hand. Yeah?
In your construction, how do you reconcile the differences in the way that quantum mechanics and general relativity treat time and return space-time? Because obviously in quantum mechanics, it's treated as a parameter that you track the evolution with the time evolution operator through. But in general relativity, it's a dynamical variable, but also it is the underlying manifold on which the motion occurs.
Yes.
So how do you reconcile these two vastly different treatments of the situation, whereas a quantum field theory would engage in a promotion of the space-time variable?
It's a great question. Actually, it is a profound question. And in fact, even the first experiment that I showed you we could do, which is, let's say, to have two superpositions and entangle them purely through gravity, even that wouldn't inform you as to what's the thing to quantize now. So to start from the beginning. Whenever you're facing a classical theory and you want to upgrade it, the question is really, what do you promote to operators? What are the quantum numbers, as Dirac called them, and what should be left as classical parameters? Many people bet you should be quantizing space-time directly. I'm going against this view. So if you really push me, like I said, we have no experimental evidence either way. But my intuition would be more that we should treat it like another field. So space-time is simply a kind of fictitious grid that we use for convenience. But ultimately, we don't really need it in our theories. Because I can always tell you, I can always refer to a point where I want you to look at the gravitational field through another field or through another object. I can put a flag there. I can say, oh, I mean the field at the point where there are 10 photons. So you see what I'm saying? So I think we introduce space-time because obviously you don't want to go through all of this referential way of phrasing things. Extremely hard to calculate and to see what's going on. So it's kind of a device to make it easier. But my intuition would say that's not what ought to be quantized. It's fiction. It's basically part of our supporting fiction. What needs to be quantized is the values of the gravitational field. And in GR you have 10 values. In electrodynamics you have 4 values of the vector potential. You put a hat on all of them and you get QED. In gravity you'd have to do this with 10 components. But it's a big question. There are many people saying, no, that, you know, if you think about physicists who have been advocating this, DeWitt, lots of Wheeler's people, John Wheeler, DeWitt, Feynman, all of them have this field theory view of that. But there are many other views. Loop quantum gravity would say, no, you need to actually quantize space-time. So this is a big debate. And it's interesting to think beyond the experiment that I showed because it's not sufficient to inform us. So what excites me is exactly the question you're asking. How do I know what to upgrade into quantum numbers? It's beautiful.
Yeah. So what parts is a passive systems in quantum? For example, like a quantum system that in principle you can have an atom between two cavities and they can talk to the surroundings of the cavities. So this part is one quantum, which is not unitary at all. And you have a
Yes, a great question. This, I think, is related in many ways. I think the only time you don't get unitarity is if you have an interaction with yet another system, which itself is unitary. So this doesn't invalidate the view that everything is quantum mechanical. What it means is that you're not controlling or bothering to access or keeping track of these extra degrees of freedom. And in fact, that's what makes this experiment even more difficult to do. Anything, anywhere, so forget controlled interactions between these two. Imagine that there are vibrational degrees. You excite phonons inside whatever is the supporting part, in the cavity, if you like. Anything else, any emissions that could tell where the system is located, of course, this leads to decoherence. So I think you really would like to do this experiment with as high fidelity as possible. In a sense, it is very similar to the problem of making a large-scale quantum computer. It's just that this is a very specific application. It should be much easier because with universal computers, you really want to be able to execute any unitary transformation. And here, I just want to be able to execute one specific transformation. But it's an extremely challenging experiment. And in fact, needless to say, I've been kind of pushing my own view here, but it's needless to say that there are people who will disagree even with the statement that I gave you just now. They will say, no, there are things which really collapse quantum mechanics and unitarity stops at some level. I profoundly disagree with them. I think when we violate quantum, and I'm saying when, I'm hoping it is not the final word, it's not going to be a return to classical physics. It's going to be something even more interesting. And the special cases will be that you will take it the same way that you take the classical limit in quantum mechanics to account for classical behavior, but it's really all quantum. The next theory is going to be related in that way to quantum. It's not going to be a return to classical physics. Again, that's my intuition. And I think the last 100 years of experiments support this 100, not a single deviation from what I'm saying. Yeah.
was wondering, so like you have these two observers who are the same location,
Yeah.
walking in different directions.
Yes.
Can't they communicate? And if they can, how does that?
They can. That's exactly right. So one thing when you dramatize these things, that's a great point actually, and it shows you when you're explaining these things, you can never really explain it in enough detail. It's a beautiful question that you're asking. So I was talking about what's simultaneous for them. As far as they now is concerned and the rest of the universe, which other events correspond to the same now. But that doesn't mean that light has traveled from these places to inform them. So even though one person on Earth coincides with the now when they made the decision, it doesn't mean they know the outcome, because you still have to wait for the light signal or for the whole army, if you like, to arrive. And then you know the outcome. But you just know that whatever happened already happened. That's the dramatic thing. But they don't know. You're right, if they knew there would be a paradox for sure, because as you say, they could just exchange these words, right? And then what? You're right. It's a beautiful point. So the way we see world, by looking at objects and then different beams of light take different times to arrive, is very different from the analysis that I was purely just formally thinking what constitutes the plane that defines now for each of these observers. It's a beautiful point. Yeah. So there is no contradiction from that. Yeah.
Oh, hey, so I probably would make a comment first before asking my question. So experimentally, in quantum experiments currently, we can shuffle coherence and purify the quantum state without opening the quantum system. And this is very important because we can approximate the unitary operation.
Yes.
And that could resonate with some of those experiments.
Yes, absolutely. So we think that anything non-unitary is unitary. That's the point of view that's affectionately known as the Church of the High Hilbert Space. And I'm a member of that church. So I fully subscribe to the fact that the whole universe being unitary is the only consistent way to even describe classical physics.
Yes,
that's the point.
Staying on the Hilbert space, and that's my question.
That's it, yeah.
So I was trying to understand how this proposal is different from geometrical quantization, where arguably quantized space and time, but...
Absolutely, yeah, that's what I'm saying. This wouldn't necessarily give you any differences. In fact, when I talk to people like Rovelli, right, who is super excited about all of these things, he claims that all of the things that they do there would in fact lead to the same effect in some of these, at least in the linear regime. And then maybe the previous question becomes important. Well, wait a second, what about the next order? What about the fact that gravity gravitates? Because gravity has energy, also generates gravitational effects. We don't know.
And I'll bring the other question is, what about the singularity theorem, for example?
Yes.
Where
that's even in the next...
they don't renormalize. So what's your hope spacing?
Yeah.
Does quantum mechanics apply that?
We don't know. But at least we need to, because remember, the controversy exists even at the basic level.
Yeah.
You know, you've got people who say, no, it's going to collapse. Gravity, that's it. It's the ultimate, frontier. And I disagree with that, and I think we ought to test it. But as soon as you see that there is a disagreement within experts, that's the thing to do. That's it. Yeah. Sorry. Yeah.
You mentioned that we're getting ever closer to testing quantum gravity experimentally. I was just wondering, which avenues of experimentation do you think are going to be first to measure such effects?
It's a good question. It's a difficult one because people again suggest all sorts of systems. It depends whether you really believe that the only way to go is to have an absolute control of that. So really make these as good qubits as we do with, let's say, cold atoms themselves. If you believe that that's the case, then probably you have to trap individual massive objects. How massive? You can do various estimates, but I think between nanogram and whatever else is there, certainly not much smaller than a nanogram. And this is already huge. No one has ever made a single spatial interference experiment with an object like that. So people talk about MV centers. Any of these complex systems that are large enough that you can identify a quantum degree of freedom, which is your handle then to do a kind of Stern-Gerlach experiment and create a superposition. But then people look at nanomechanical oscillators. They say, don't worry about it. Just look at two oscillators. they will build up a phase as they oscillate, and if you can really discriminate that from any other effects, that's already a kind of confirmation. So maybe we get some indirect confirmations first from messier systems before we really go fully and do it conclusively. That's how it seems to me. I'd love to be the first to do it. I really want. There are 5 or 6 groups, I think, racing now. And I think it's just a question of time and money, I guess, right? As anything else here.
A lot of what you've said to me sounds like it has somewhat of a holography inclination.
Nice.
I wanted to know if you have an opinion on radiosity correspondence and in general gauge gravity dualities.
I don't know much about. I love that direction because I think it featured very strongly even in many body systems. So I think there were many results that were derived there that actually ultimately became interesting for condensed matter and describing phase transitions and all of that. And that's beautiful. I think the crosstalk between condensed matter and high energy. It could well be that if quantum mechanics is really correct at that level fully and it can account for these things, it could well signal some kind of holography through entanglement, as we know. So it's really all about different regions, how they get entangled, and what does that really mean for the mutual information between these regions. I think my only concern would really be that lots of these directions, as far as I'm aware, have a life of their own, in the sense that people explore all sorts of other questions that may not directly be relevant. So it's not clear to me what, if anything, would survive from these ideas, but I like that a lot as well. So it could even be that gravity is some kind of force that's generated by some other, let's say, quantum fluctuations, and you could even that's consistent with this kind of entanglement. So forget space-time, forget gravitational field, actually there isn't such a thing. It could be a quantum effect, even theories of this kind exist. It could be induced by something else. That's kind of the idea. And none of that has been tested. Yeah. Lots of jobs for us physicists, right? That's the good news.
Do we have any further questions? Thank you very much for your time.
Great pleasure.